This is problem 33 from the electromagnetic induction section. In this problem, we have a 100-turn loop of radius 1 centimeter, initially 50 centimeters away from a very long straight wire carrying a current of 250 milliamps. Let me write a few things down. So before I forget, I want to use the 100 turns in the area. And so the area is equal to 100 times, this is a circle with a radius of 1 centimeter, so the area is pi times 0.01 squared. Okay, with the 100 turns, which I like to put down because if I don't write it down right away, I have a tendency to forget to include it. Okay, the flux is equal to the integral of B dotted with dA, but because the 50 centimeters, which is the distance from the long straight current carrying wire to the center of the loop, is much, much greater than the 1 centimeter radius of the loop, we can treat B as being uniform inside the loop, which means that this just becomes B dotted with A and not have my area vector there. I need my magnetic field vector. The magnetic field where the loop is pointing out of the page. If you stick your thumb in the direction of the current, your fingers are pointing out of the page where the loop is. So let's say the direction of the area vector is pointing out of the page in the same direction as the magnetic field. So when you do the dot product here, you just get B times A. The magnetic field is the magnetic field from a long straight current carrying wire, so that is mu naught I divided by 2 pi times the distance from the wire to the center of the loop. And let's call that distance y. So that distance is y. Okay, so then my flux is equal to mu naught, I was going to also write down the current is equal to 0.250 amps. I don't even think I finished reading the problem. So it says if the loop is moved away from the wire with an initial speed of 10 centimeters per second, what is the initial induced EMF in the loop? Okay, so the loop is moving away from the wire. The flux is equal to mu naught times I divided by 2 pi y times the area, which is 100 times pi times 0.01 squared. Okay, so now we have our flux. The loop is moving away, so the distance that we have here, the y, is going to change as the loop moves away. So we don't want to plug in the 50 centimeters because that's just the initial value for y. So we can say y initial is equal to 50 centimeters. Oops, 50 centimeters. But that distance is going to change as we move the loop away from the wire. Okay, so after finding the flux, the next step is to find the EMF, which is the negative derivative of the flux with respect to time. And mu naught is a constant, so when I take the derivative with respect to time, I can pull the mu naught outside. I can also pull the current outside because the current is staying at 0.250, so we're not changing the current. We have a 2 pi in the denominator. I can pull out the 100 because that is a constant, and the radius of the small loop is not changing, so I can pull that outside also. So we're left with a derivative with respect to time of what's left is just 1 over y. So I have to take the derivative of 1 over y with all this other stuff still out front. Let's just do this off to the side. Well, it's the derivative with respect to time. So first I take the derivative of 1 over y with respect to y, which is negative 1 over y squared, but I took the derivative with y. I was supposed to take the derivative with respect to time, so I have a dy dt after multiplied by the negative 1 over y squared. Now, the dy dt, that's how the position is changing with respect to time, which is, thinking back to Physics 161, our speed. So dy dt, that's what the 10 centimeters per second is. So let's write that over here. Dy dt is equal to, well, 10 centimeters per second, that would be 0.1 meters per second. Okay, so now we're going to take this and put it in here. And so we have negative mu naught over 2 pi 0.250 100 times pi. Let's cancel that pi and that pi. And we have a 0.01 squared. Now for this, we have negative, so that's going to make that positive. We have 1 over y squared. And we have a dy dt. Dy dt is equal to 0.1 meters per second. And they say the initial induced EMF of the loop. So as you pull the loop away, y is going to change, so the EMF is going to change. But initially, y is equal to 50 centimeters. So now we can plug all of that in. So we have mu naught times 0.250 divided by 2 times 100. I guess we could call that 50. And we have a 0.01 squared, a 1 over y initial, which is 50 centimeters or 0.5 meters, and the dy dt is equal to 0.1. So plug all of that in, and you should get a 6.28 times 10 to the negative 10th, and the units for EMF are volts. So that all works. Now, it worked very nicely, but it's worthwhile to check what the direction of the current is. So this came out positive, which is good. And if you go back and look at the drawing, the magnetic field was coming out of the page up here. As you move the loop further away, the magnetic field is going to decrease, and so the flux will also decrease. The magnetic field is decreasing because it depends on how far away you are. The farther you are away, the weaker the magnetic field is. If the flux is decreasing, the induced magnetic field should be pointing in the same direction as the initial magnetic field, so the current should be going this way. But if we said the area vector is pointing out of the page, then that's the positive direction for the current. So the current's going in the positive direction, and so everything worked out correctly. If the current happened to be going in the negative direction, if you didn't think about it ahead of time, you'd probably get something negative for the EMF, and then it would be worthwhile to go back and check why it's negative, and usually that comes in from how you defined your area vector. Also in this problem, I didn't really mention it at the time, but we have a dy dt here, which I said was equal to the speed. And y is increasing, so dy dt would be positive. But if you are moving the loop closer to the wire instead of further away from the wire, then dy dt would be negative because y is getting smaller. So there's another sign that could come into play. Okay, so that concludes problem 33. And I realized that I forgot to square the y in the denominator. It was squared here. I didn't write the squared there, but you would still get 6.28 times 10 to the negative 10th volts when you square that.